Hi there and welcome to part 15 of our C tutorial series. In this part we're going to look at files. Now you know what files are. And the interesting thing on Unix is many things are files and can be opened as files. So actually file I/O goes way beyond just opening a text file to write or read, for example. There are two primary types of file available, or no, let's say there are two primary file access APIs in Unix. The first one uses a file structure, and all of the API operations are, well, most of them are prefixed with an F. So to open a file, you use the function fopen, and this is in standard io.h. So all of the functions that are prefixed by an F that operate on a file structure are part of the C standard and are more portable. They are also buffered. The other way to open a file is returns what's called a file descriptor, which is an integer, and a lot of the functions have the same name, but they don't have an F in front of them. These are system calls. Something like open does offer you more control over fopen around various flags on opening the file and permissions and things like that. And in some circumstances you would want to use this. At the moment you don't need to know that, because by the time you get to the point where you're programming something and you need to know in which circumstances you might prefer to use this, you probably won't need me to tell you. So what I'm saying is it's not that critical at this point. So we're going to look at the file operations that return a file structure. These also have the benefit of, besides being buffered, and what buffered means is that when you say read from a file on the disk, the API will go ahead and read more than you ask for, and it will buffer that in memory. Because disk I/O is slow compared to memory access, if you're dealing with large files, you should see a performance increase. But of course, the kernel itself often has buffers, so you know, but ostensibly this buffered I/O is faster. Now, so before we look at opening kind of traditional files, like text file, I just want to note three special files which we've actually seen before in some of our tutorials. Now, these are standard in, and typically this is, well, ordinarily when your program starts, this is mapped to the command line input. So the terminal that you execute it from, it will be assigned to the terminal's output, essentially, i.e. what you type in. And this will be line buffered by default. So that means that this will be flushed, the data that you input from the terminal will be flushed to your program whenever there is a new line character, and that should be platform independent. Yeah, it will be platform independent. There is also standard out, which again is line buffered. So if you do a write to standard out and you just write a few characters, you won't see them on the standard out until you send a new line character, or until you explicitly call flush, which will send those characters. And there is standard error. Standard error is not line buffered by default, but you can change that. Now the reason these have a kind of default buffering behavior is because they can be changed. So if you, for example, pipe the output of a program to another program, then the second program's input essentially replaces standard out. So then the behavior will not be line buffered. So these three things are special files. And when you use printf, you write to standard out. When you use something like getC, which we saw before, you read from standard in. Now, you're going to find this pretty simple. So to open a file, a text file, we can use the following arguments. And I will just put the arguments here because obviously I can't fit them in there. So the first argument is the name of the file. So a name in the current directory might be ./hello.txt. And this is obviously quoted. And then the second argument is how you wish to open the file. And there are three primary options. You can either open the file for reading, and that's how you do that. You can open the file for writing, and you can open the file for appending, which means that when you do a write, it will start at the end of the file. And some files can only be opened for appending if their permissions are set on Unix. So they're the three primary different types, but you can also you can open a file for reading and writing. And in fact, in any of the modes, so either in R, W, or A, you can append a plus to say that you want the file to be opened for both reading and writing. So A plus would mean you're appending to the file, because what I should mention is that the file, when you open a file, the kind of file pointer has a position in that file, and when you do a write, it'll write at that position. When you open a file for writing, you will begin at the start of the file, so anything you write will essentially overwrite whatever's at the start of the file. You can move around in a file using seek functions, whereas with A, you're going to start at the end of the file to append. But so for A, you can put a plus and you can then also read from that file. For R, you can put a plus and then you can also write to that file. And for W, you can put a plus and then you can also read from that file. So the plus just means you can read and write. It always changes it so you can read and write. What you can also add to the characters you put in here is you can append a B. Now, what this was for was to distinguish. What this means is that you're opening the file in binary mode. Now, this was to distinguish for the purposes of cross-platform compatibility whether or not you're opening a file up in text mode or not. And the reason that's important is because on different systems, the characters used for line endings are different. On Mac, Windows, and Unix, they are different. Whereas some of the functions print a new line, or something like getLine looks for those end-of-line characters. And in order for those to behave consistently, the implementation needs to be different on different systems. So what that means is that certain functions behave differently when there are new line characters present. The B explicitly states that you do not want any line mangling to happen, any interpretation of those characters as being special. Now, so the recommendation would be, if you're opening a file for text manipulation, use W, or whatever it is, R if you're reading, and if you're opening it for binary manipulation, then put a B afterwards. But on Unix, let's take the example of FreeBSD specifically, then there's no distinction, and files are always opened in binary mode because FreeBSD knows what a new line is, and it's a single character on FreeBSD. So there's no difference when you're using fopen. The only difference that occurs from opening in binary mode is if you use fmemopen, because you can open a buffer as a file. And then on Unix systems, when you do a write into the buffer, it will append a null character if you open it in text mode, whereas it won't append a null character in binary mode. So I guess from that rather long-winded kind of explanation, if you are explicitly opening a file for binary manipulation, you should probably append a B just for the sake of readability, even if there is no explicit distinction. There you go. So to close this off, that's our arguments. And that's all of the arguments, and then that will open the file hello.txt for writing, in this case in binary mode, which will also create the file if it doesn't exist. Once the file is open, we can then use some of these f-prefixed functions to do useful things, like we can use fprintf, and we pass in the file handle, pointer to this file structure, and then we could print hello with a new line character. So we're opening in text mode, so let's follow my own advice, and we're opening it just for writing without a binary postfix. And then once we're done with the file, we call fclose and pass in the file handle. And then we're done. So that's how you open a file and write to it. It's pretty simple. So I think at this point, we should look at an example of that. So we're going to do something very simple. We're just going to open a file, write hello to it, and then close it. But we're going to be relatively robust about it. We need standard io.h, because that's where the file operation stuff is. And it really is worth looking at man standard io. And just give yourself an overview of the buffered stream input-output interface that the file structure and associated functions provides. Also, read man fopen. We're going to need standard lib.h because we're going to use the exit function when things go wrong, and we're going to need error number.h because we want to see what the error is when things go wrong, although there is only one error. So we create a file, we'll give it an initially null value, then we're going to call fopen on it, and what we'll do is we'll say, and we're going to make it const, wow, and the file name is going to be test.txt. So we're going to open our file name, and then we're going to pass in what we're going to open it as. We're going to open it for writing. And when we do this on a file that doesn't exist, that will actually create the file. So our file is now open for writing, or maybe it isn't, maybe something went wrong. So if f equals null, something went wrong, in which case we're going to fprintf to standard error, and we're going to say error opening s for writing. I'm just going to let this wrap round. Error number D, and we've got our file name and our error number. And of course then we need to put in our error number and set it to 0 before we call fopen. After we've done that, if things went wrong, we're just going to exit with a non-zero exit code status. By the way, exit will close any open file streams. Of course, we don't have any open ones at this point. If everything went well, we're going to use fprintf, this time with our file handle f, and we're just going to print hello there and a new line character. When we're all done, we're going to cause fclose and try and close our file. Now, we can again check if there's a problem with fclose, but since we're exiting anyway, there's not really anything we can do. And let's compile that and run it. So this should create a file called test.txt. But let me just show you what we've got there. Ignore those MKV files, that's the video recording. Normally do it in a different directory. We haven't got a hello.txt, so let's now run it. And now we've got our test.txt, sorry, not hello.txt. And if we have a look in there, we can see that it says what we've written. So it's actually very simple. Let's try and demonstrate an error. If I delete test.txt, and now if I try and run the program again, but this time try and open it for read writing. By the way, you can put the R before or after the W. You can also do W plus, which means, and if you put a plus in front of either the R, the W, or the A, it means the file will be open in read-write mode. I prefer to use that string if I'm using read-write because I think it's more obvious, but it's up to you. Now, what do you think is going to happen if we try and do that? Well, we get an error. Error opening test.txt for writing, error number 2. Now that will actually be, if we look at what fopen returns, null is returned, and there's only actually one error, which is called einval. The mode argument was invalid. So we could check if it's equal to einval, but there's only one error that can occur anyway. And the reason it's invalid is because we've tried to open a non-existent file essentially for reading. It's okay to open it for writing if it doesn't exist because it'll be created, but we can't open a non-existent file for reading if it doesn't exist. Now if I change it back to writing, run it again, so that now we've got test.txt created, now we try and open it for reading and writing, so compile it again. Actually, there's no problem. Now you might expect then, because we've reopened it, to see hello there twice in the file. But it's only there once, and that's because whenever we open this, if we look in the manual, the stream is positioned at the beginning of the file, so we're just overwriting it. If we wanted to append to the file, we'd have to use A. So let's give that a go. So if we use A, compile it, run it again, and now cat our file, we'll see that we've added an extra line onto our file.
So fprintf is one way to output to a file in a way that uses the same kind of familiar notation of printf. There are different ways to write to a file and to read from a file. We're going to look at a method of reading from a file that also uses the kind of familiar format specification of printf, and it's called fscanf. Now some people don't like this function, and some people will even go as far as to say to not use it, like as if there's something inherently bad about it. There isn't. And most of the time when you hear people saying things like that, in fact almost all of the time, just ignore it. It's just nonsense. It's just absolute nonsense. You can use fscanf safely, and you can use it in a program. It's not going to make your program blow up. So fscanf takes a variable number of arguments like printf does. And let me show you what those arguments are. So the first argument is the file. The next argument is a format string. And what fscanf is doing, it's reading from the file. And in the format string, we write, using the ordinary percent modifiers, the type of things that we're expecting to read. So if we want to read an integer, we put a %d. So say we want to read an integer and we know that that integer is followed by a new line in our file. Then we do this. Then the next argument that we put is a pointer to a variable within which to store this integer that's read. So if we've got an int x here, then we might have the address of x here as our pointer. And then that would be in this case 3 arguments. We've got our file, our format specification string, and the variable. And we can have as many format specifiers in this format specification string as we want. So if we knew that we were reading a file that had 5 integers per line, then we could have 5 of these in a row. Or we could construct the string that had the correct amount of arguments to read, or something like that. This is quite convenient sometimes because, of course, you might have earlier done an fprintf where you actually wrote out your integer to the file, whatever it is, let's call it b or integer b. And then the format string that's used to read in the integer that you've written out is the same as the one that you're using to read it in. So in that sense, I think fscanf is useful for basic kind of file configuration files and things like that, and simple kind of text-based files. It's actually, I think, a very useful function, and I ignore anybody that tries to dictate to me what functions I can and cannot use in my programming, without any rational basis, essentially. So that's fscanf. Let's take a quick look at fscanf. So what we're going to do is we're just going to create a new file, and we're going to open a file called temp.txt for writing. So we're going to create this file. We're then just going to fprintf something, a couple of numbers, let's say 55, 33 and 22. Now we're going to close the file. So then that will create our file. We're now going to reopen the file, and I'm not going to, for the sake of brevity, I'm not going to bother with checking that the file is actually opened and everything like that. We'll just assume that's worked. But of course, when you're writing a proper program, please put that stuff in. So we're going to open temp.txt, this time for reading, and we're going to do fscanf, and we're going to read in our 3 integers. And of course we need somewhere to store these integers, so let's just use the values a, b and c, or the variables a, b and c, and we'll give them values of 0, just so that we can tell that they have changed. Now we need to pass in the address of a, the address of b and the address of c. And what I'm going to do is I'm going to say matched items equals 0, and then we're going to get the number of matched items from fscanf so you can see what it does. So we can say fscanf matched items so we're just going to print out the number of items that were matched, and then we're going to print out these items and check that this works. Of course, we've got to close off our file at the end of it. So let's have a look. Let's compile that, and oh yeah, there's something pretty obvious here. Into fscanf, I haven't provided the file, so we've obviously got to pass fscanf into. Let me just do this. We've got to pass fscanf. We've got to pass into fscanf our file, obviously, because that's what we're passing. Right, let's have a look. Okay, we've still got an error. Okay, yeah. Again, I've made the same mistake and forgot to pass our file into fprintf. Obviously, we need to know what we're printing to. So let's compile that and just run our fscanf. And we can see here fscanf matched 3 items, and we had 55, 33 and 22, which is the values that we printed out. So you can see that fscanf is quite useful for reading in things that you've printed out. So let's take a look at what happens if we mess this up. So if we replace the number 33 with 2 A's, what's going to happen there? Let's have a look. So to explain what has happened here then, we've only matched one item. So fscanf is going to try and match the characters exactly as they are seen. So this space it will match, and then it expects to see two A's. So immediately that has failed, in which case the whole thing fails and we don't process the rest of the string. And if we look at the man page for fscanf, in the return values we can see these functions return the number of input items assigned, which can be fewer than provided for or even 0 in the event of a matching failure, which is what we just saw. So this is why it's not necessarily the best method to use for reading input. I mean, if you remember from the last episode, we looked at string to long for parsing, extracting a number from a string, and string to long told us exactly where it failed. Whereas here, if we were trying to read these three numbers in and the file had somehow got corrupted, all that we would know at this point is that fscanf failed, and it failed after matching one item. Of course, we could then look in the file and we kind of know where it is, but it might be quite difficult to... So we don't really have as much information, but still fscanf is useful, and I wanted to illustrate its use.
So say we expect in our file, and I'll try and pick something that's realistic. We might have an option like speed in some configuration file. So we might want to match the string speed, colon, and then a space, and then an integer. What will happen is fscanf will look for these characters, and it will expect to see them in the string it's processing. It will fail immediately as soon as it mismatches a character. So our file that we're reading will have to have these characters. It will have to have a colon. When it gets to space, spaces are treated differently. All white space is treated as equivalent by fscanf, which means that we could put 1,000 spaces here, we could put a new line, so new line is also classed as a space, or a tab in there, and it would still keep parsing until it got to here, until it got to a non-white space character, and then it would expect to see an integer, and any character that's not part of an integer will cause a match failure. So that's fscanf. There's a whole bunch of things you can do, and if you read the man page you can learn about it. We can perhaps understand some of the criticisms levied against fscanf by considering what it returns when we get a mismatch. I mean, we just get a mismatch and we get returned the number of things that were matched. And if we compare that to string to long function, which we looked at in the last episode, we actually got a pointer to exactly where in the string we failed. Another thing worth pointing out with regards to file access, imagine this is our file and our bytes kind of go in rows like this. The file structure contains a pointer within it which points to where its sort of current reading head is. So if we imagine these are bytes crudely drawn, very crudely, and we're originally here. If we do fscanf and we read a couple of digits, like perhaps the number 32 was in here, and we're processing a fscanf string that looks like this. After it's processed these digits, the internal file pointer will point to here. So the position in the file is advanced for any read operation like fscanf. You can move this head around as well by using fseek, which I'll leave you to look up. So we just saw essentially two symmetric operations. You've got fprintf, which can print a formatted string to a file, and fscanf, which can read from a file using a formatted string as a template values into variables. To finish this off, we're just going to look at a couple of other useful symmetric functions essentially, which are called fread and fwrite. And these functions allow you to write binary data or arbitrary data to a file. So let's take a look at
fwrite. We'll start with fwrite. And I'm going to kind of paraphrase the function prototype using my own names for the variables that are more readable. fwrite returns size type. A size type, we've not actually explicitly talked about this before, but malloc takes a size type, size of operator returns a size type. It's an unsigned integer, that's all it is, and that's all that actually matters with regards to this conversation actually. The reason it was invented and that it isn't just an unsigned int is for portability, that on different architectures the amount of memory you can address can be different, and the amount of objects that you can read or write, it might be different. So this was designed for portability, and that's all I'm going to say about it. So it returns a size type, and it's called fwrite, and what this is going to do is write a block of memory to a file. So the first argument is a block of memory, and it is a void pointer. I'm just going to call that source. The reason it's a void pointer is because we don't care about the type of that block of memory, because all fwrite is going to do is going to write out however many bytes we tell it to, and it's going to go, as long as that's a valid memory address, it's just going to go there and copy those bytes. How we specify the number of bytes to write is determined by the next two parameters. The first this is done so that we can specify an object size and a number of objects, so it's kind of for convenience. So the first argument is another size type, and it's the object size. So I'm going to just call that object size. And then the next argument is another size type, and it's the num objects. So the number of objects. And finally then we have our file parameter, because we need to know what we're writing to. So that's just to be clear, that's a curly bracket. So just to go over that, we're writing to a file. This is what we're writing. So this is a pointer to the memory address that we're writing from in our program. That might be a buffer, that might be a character buffer, or anything else like that. It could be an array. And this is the object size, and combined with the number of objects, that tells us how many bytes to write. So say we have an array with 50 pixel structures in it, if you remember from the tutorial on structures. Well, the object size is going to be size of pixel, so size of that structure, and the number of objects is going to be 50. And then fwrite will use that to calculate the number of bytes it needs to write. To give another example, say we had a character buffer here in source, and we wanted to print out the first 5 bytes to our file. Then we could actually calculate that in two different ways. We could say the object size is 5, and that there's 1 object to write. Or we could say that the object size is 1, and then there's 5 objects to write. So this is just used for the calculation of how many bytes fwrite needs to put out. And of course the file is the destination that we're writing to. fread is the kind of analog of this, or the dual of this, and it's like this. And instead of source, we have destination. So the thing that we're writing, that we're reading from the file. Where do we put it? We put it to here, and then again we need to know how many bytes we're reading, and then the file that we're reading from. Sorry, that's obviously file pointer. So that's it. That's fread and fwrite. So I'm going to show you a demonstration of those now. So we're going to begin by opening a file called test2.bin. We're going to have a binary file, or at least acknowledge that it is. I'm going to open this file for writing in binary, just to be kind of explicitly clear. We're going to provide that B specifier even though we don't need to. Now what we're going to do is we need some data to write. So what we can do is we'll quickly declare a new structure called a pixel, which contains unsigned int r, g and b, and we will have an array here 50 of these things. And we want to write that out. We should probably give it some values. We'll give the green value, make the green value equal to I. There we are. Now we open this up, and then we're going to use fwrite to output these values. So fwrite, of course this returns a size t type, objects written equals fwrite. I'll do this like this, and we are writing, we want the address of pixel array. We are writing 50, well, the size of pixel is the object size. We're writing 50 of them, and we're writing them to our file f. Once we've done that, we can close our file. So let's see what's happened here. Can't see any output, of course, because we didn't really do anything, but we can see our file test2.bin. So let's have a look. Test2.bin. It is 600 bytes in size. Does that make sense? Well, we've got 50 pixels. Each of these is 4 bytes, so that's 12 bytes. 12 times 50 is 600 bytes. Correct. If we took a hex dump of our file, yeah, you should be able to see that every third byte is essentially changed, because we were changing only this value, the rest are all 0. So that's how we write those objects. We could now read them back into a different pixel array. So we could have pixel array 2. And we're just going to basically just copy this. So we open the file again, this time for reading. Sorry. I'm going to read bytes. We're going to read in pixel array 2, so we need the address of pixel array 2, and it's still size of pixel, and there's 50 of them. We're reading from f. Just to check this has worked, we're going to go through and print these out. And tell you what, we're going to print pixel array to, first of all we're going to print I, then we're going to print the red value, the green and the blue. And that's it, right? Let's compile that. Oh yeah. We've already defined these things, we can't define them again, so we get rid of those declarations, recompile. Oh, we've still got a error here. What's this? 4016 pixel array 2. Yeah. We need to provide an index. Okay, cool. Yep. There we go. So we've read it back in successfully. And these are the values that we expect to see. And something I forgot to do is we've got this objects written here. And if we can print that out. And I'll tell you what, I'm just going to comment this out. You can do a multi-line comment like that, by the way. I just want to check that. Yeah, fair enough. To be fair, it is an unsigned int. So we should, well, here it says it's an unsigned long. which is correct. It's a 64-bit long on this particular machine. Now what? Yeah, what's happened there? Why is that? That's not terminated for some bizarre reason. Anyway, there we go. Objects written 50. So if there was any error writing those objects, the objects written would not be 50. So we'd be able to tell there's a problem. So that's how you deal with the error handling. And of course, check out the man page to see what's returned in the case of error.
So there you go, that's fread and fwrite. I would encourage you to go and look at the man page for sdio.h, standard.io.h, and look at the man page for fseek and things like that. There's quite a lot of functions. You can get characters, you can even unget characters and push them back onto the stream, which is quite useful to allow you to kind of peek ahead and things like that. Otherwise, I hope that was useful, and I'll see you next time.